Hello, today I'm going to teach you all about vectors and matrices as intuitively and simply as I can. So, this might be a fairly long video, so I'll attach timestamps down in the description if there's any parts of the video you want to jump to. So, let's get started. So, by definition, a vector is something with both a direction and a size. So the easiest way to see this is as an arrow, just like what's on our screen. You can see this arrow has a direction, it's pointing to the top right, but also you can see it's got a size associated with it. But if I were to ask you a bit more about this vector, for example, how much to the right is it pointing, or how much upwards is it pointing, or what even is its length, just by looking at it, it's quite hard to tell. So what we need to do is we need to rewrite our vector in terms of other vectors whose directions and lengths we know to put out a vector in a coordinate system. And you'll see what I mean in just a moment. So, in our 2D space, so our screen, all we need is two vectors to create our coordinate system. And the vectors we choose is one which direction is to the right, called x, and one whose direction is upwards, called y. Now you may think, well, can we pick any two vectors to use? Well, we have one condition. We want to make sure that both vectors have completely different and independent directions. And what I mean by this is, let's say in this example, we take x. It doesn't matter how many x's we add on to each other, we will never go in the direction of y. Right? Because x takes us left and right, but that can never make us go up or down. Which means both vectors' directions are linearly independent. So when we create our basis vectors, we call them, which are our two vectors which will create our coordinate system, we first of all need the same number of basis vectors as there are dimensions. So for instance, if there's 3 dimensions, we would need 3 basis vectors, but they also all need to be going in completely independent directions, as in are all linearly independent. So by default, we set our basis vectors to have lengths 1, because this makes calculations later on a lot more simple. Now, this notation here of an arrow, the line with an arrow, means vector, and you specify what the vector is with whatever you write in the middle. So in this instance, it's an x surrounded by the arrow, so we call that vector x, and that's what I'm going to use to refer to the x basis vector. However, down below, you see there is a y encased in the vector. So that just means vector y, which we'll use to refer to the y basis vector. Now, you may think, well, what about going left or down? Well, as a general rule of thumb, if you travel in the same direction as the arrow, i.e. you travel in the same direction as where the vector's pointing, you're traveling a positive amount of that vector. But if you travel the opposite way to where the arrow is originally pointing, you will be traveling a negative amount. So traveling to the left means to travel a negative amount of the x basis vector, and traveling down means to travel a negative amount of the y basis vector. So let's take our vector here, which was from the start, and let's put it in our coordinate system. Now we can see now quite clearly that it has 2 unit lengths to the right, which means it has 2 of the x basis vectors. And then it has 3 units of length upwards, which means it has 3 of the y basis vectors. And this is remembering that each of the x and y basis vectors have length 1. So to have 2 lengths to the right means to have 2 of that basis vector, which is x in this case. Now we can write this as a column, where the top element shows us the amount of the first basis vector, and the second showing us the amount of the second basis vector in our vector we are looking at. And we can write this also using our arrow notation from before, as 2 lots of the x basis vector plus 3 lots of the y basis vector. Now, we can also add in a third basis vector. So by default, we say the first basis vector is always x, the second basis vector is always y, and the third basis vector, if there is one, will always be z. So you can see we've added another independent direction here. So think of this as going into the screen. I know it's quite hard to draw it, but think of it as going into the screen you're looking at. And we can write this once again as a column. There's 2 amounts of x, 2 amounts of y, and 1 amount of z. Now, what if we wanted to calculate the length of our vector? Well, if we look at the top here, we can see our vector, if we break it up into its part going to the right and then upwards, it makes a right-angled triangle. So we can use Pythagoras' theorem to calculate the length of this vector. So the length of this vector is simply the hypotenuse of the triangle, with the other side lengths being a, the amount of the x basis vector, and b, the amount of the y basis vector. Which means if you square a and b, and then take the square root, so square root of a squared plus b squared, we'll get the length of our vector. Now when we have our vector written as a column, it immediately tells us the amount of the x basis vector and the amount of the y basis vector. So we can immediately square each component, add them together, take the square root, and get our length. And this is the complete same in 3D and upwards. The only difference is we would be having another component of z. So our length would be a squared plus b squared plus the amount of z squared, which is c in this case. And this is a brief example with 3. You just square each component, add them together, and take the square root. So when you add vectors, the way you can visualize it is by traveling the first vector, and then from that endpoint, traveling the second vector afterwards, as shown by this diagram. And then, if we have them written in column form, we can simply add both columns together. And the reason behind this is you're simply adding together both vectors' basis vectors. So for example, if this one has 3 of the x basis vector, and this has -2, our resulting vector will have 3 minus 2, which is 1 of the x basis vector. If the first has 1 of the y, the second has 2 of the y, the resulting will have 3 of the y, and likewise with the z. So when we take away vectors, there's 2 ways to think about it. The first way is to travel the second vector, and also afterwards travel the first. So you can see here we've traveled the second and we've traveled the first, and we want to see what vector takes us from the second to the first. This may be a little bit confusing to think about, but there is a simpler way afterwards. But the way we quickly calculate it in terms of columns is just like before, where we added the basis vectors together. Now we're simply just taking them away. So if the first has 3 lots of the x basis vector and the second has -2 lots, our resulting will have 3 minus -2, which is 3 plus 2, which is 5 lots of the x basis vector. Then with the y, if the first has 1, the second has 2 amounts of the y, the resulting will have 1 minus 2, which is -1 amounts of the y, and the same for z. But a simpler way of thinking about it is as adding the negative of the second vector. So just to clarify, if before we were taking away this vector -2 to 0, we can apply the minus to each component of this vector, and then the equivalent would be our original vector plus this vector with everything minus. So as you can see here, 3 and 1 plus, and we've added a minus to each component, which gives us this vector, which happens to be like the mirror image of our original one. So then, doing the same way of addition, we travel the first, and from the end of the first, we travel the second, which will take us down here. And then, if we want to add it just in terms of columns, we can see 3 plus 2, 5, and the same with the others. So we can also multiply our vectors by a constant. So, for instance, if we take our vector, which has 2 amounts of x, 2 amounts of y, and 0 of z, multiplying it by 2 simply means to multiply the amount of each basis vector by 2. So our resulting will have 2 times 2, which is 4x, 2 times 2, 4y, 2 times 0, which is 0z. And if you want to try and visualize it, all it does is it keeps our vector in the same direction, but it multiplies its length by whatever this number is here. So in this instance, it doubles its length. So now let's look at matrices. So matrices change the current basis vectors, which by default we've said are x, y, and z, to whatever its columns are. So the first basis vector, so x, will change to this column, the first column. Y will change to the second column, and z will change to the third column. Right, so all we've done here is we've separated this big chunky vector into 3 individual column vectors. Okay, so the first element, so if we zoom into the first column, 1, 0, 0, the top element shows us the amount of the first current basis vector, which is x, in our new first basis vector. Then the second element shows the amount of the second current basis vector, which is y, in our first new basis vector. And the third element shows us the amount of the third current basis vector, which is z, in our first new basis vector. So in simple terms, this shows us the amount of x in our new first basis vector. This shows us the amount of y in our first new basis vector. And this shows us the amount of z in our first new basis vector. And just to clarify, the first current basis vectors are always going to be x, y, and z. So what we can do here, what I've done is I've rewritten our matrix from before, but I've included the vector for x basis vector, y basis vector, and z basis vector. So you can see clearly what I'm trying to convey. So if you were to look now, we see the first column, 1x, no y, no z. So the first new vector is just 1x. The second is just 1y. And the third, oh, that's supposed to be a 1 there, is supposed to be, 1z. So if you notice, that means this matrix doesn't change our basis vectors at all, because by default they were x, y, and z, and this simply makes them also x, y, and z. So a cool consequence of that is any vector you apply this change of basis vectors to, well, will stay unchanged, which is quite obvious because the matrix itself doesn't change the basis vectors to anything. But if we want to quickly look how we'd calculate this, remember, a vector means the top element tells us the amount of the first basis vector. Now, this matrix has changed the first basis vector to, well, I guess it hasn't changed, but we'll have more examples a bit later. But it set the first basis vector to 1, 0, 0, which means this vector has 2 amounts of that first basis vector, which is 1, 0, 0, 3 amounts of the second, as shown here, and 4 amounts of the third. So this is a nice sort of cheeky way to link together the definition of each element of a vector with our matrix, because usually matrix multiplication is taught a little bit differently, but this is what it actually means. So this is a little bit more of a tough example, I suppose, but let's crack into it. So this is simply telling us that the first new basis vector is 3x, 3y, and 1z. The second is 4x, 6y, and 2z. And the third is 2x, 3y, and minus 1z. Now I've tried to draw them here. So as you can see, the dashed lines are our old basis vectors, x, y, and z. And these 3 lines are our new ones. So when our vector says we travel 2 units of length across the first basis vector, whereas before that would mean 2 units of length across x, now our first basis vector is 3, 3, 1. So here, after we've changed them using this matrix, this 2 here means we travel 2 units of length along this new first basis vector. And as you can see, that'll cause this vector to be completely different. As you can see, it has 2 amounts of 3, 3, 1, the first new basis vector, 3 amounts of the second new basis vector, 4 amounts of the third new basis vector, and if we add them all together, we find our transformed vector in our new sort of coordinate system with different basis vectors has 26x, 36y, and 3z. So that's a massive change from what it was when it would have otherwise been 2x, 3y, and 4z. So now let's look at an example which you'd be much more likely to see if you were studying maths, maybe at, I think this would be probably A level, maybe further maths. So what you would see here, we have a 2D vector this time. We're sort of scaling it down a bit. But let's have a look at what this matrix is telling us. It's telling us the first basis vector is now 0x but 1y. So it's changed our x basis vector to be the y basis vector. But then it's changed the y basis vector to be minus x, 0. So it's changed the y basis vector to be the minus x basis vector. So what it's done is it's rotated our basis vectors 90 degrees anti-clockwise, because the x has turned into the y and the y has turned into the minus x, which means any vector we create out of those two basis vectors will also be rotated 90 degrees anti-clockwise, because the components that made it up were rotated in the first place. So a nice little thing to remember is that when you apply a transformation to a vector, that's the same as applying that same transformation to its individual basis vectors. So if you want to calculate this out properly, this vector tells us that we have one amount of the first basis vector and we have one amount of the second basis vector. So when we add them together, we get the vector minus 1 in the x, 1 in the y, which is, compared to our original 1, 1, rotated 90 degrees. So this is the 90 degree anti-clockwise rotation matrix in 2 dimensions. So now there are some rules we have to go over when considering applying matrices to vectors and whatnot. The first is that the matrix always has to be on the left of the vector. And this is because usually in class they'll teach you a different matrix multiplication method which sort of requires your vector to be on the right. Using this method, obviously it doesn't really make much of a difference, but this is the way they would like you to write it. The second is that the matrix has the same amount of basis vectors as the vector you apply it to. What I mean by this, look at this matrix. It has 2 columns, which means it has 1, 2 basis vectors. It sets 2 basis vectors. Our vector has an amount of 1, 2, and 3 basis vectors. So our matrix sets 2 basis vectors, but our vector has 3 basis vectors. Because there's a mismatch, we don't know what the third is given by this matrix, which means it doesn't work. Sort of similarly, in this example, our matrix sets 3 basis vectors. You can see 1, 2, 3. But our vector only has 2. So again, there's a mismatch, so it doesn't work. So the amount of basis vectors the matrix sets has to be the same as the amount of basis vectors the vector has. Now, an easy way to remember this is the amount of basis vectors our matrix has is simply the number of columns it has. The amount of basis vectors our vector has is equal to the amount of rows. So for you to be able to apply one matrix to to a vector, the amount of columns in the matrix has to be equal to the number of rows in the vector. So for example, in this instance, the matrix has 2 columns, the vector has 2 rows, so it's good to go. Okay, so now let's look at successive transformations, which is where it gets just a little bit more confusing. So as you can see here, we're changing our basis vectors twice. So first of all, let's ignore this one, right? We start with the leftmost matrix first. So by default, our basis vectors are x, y, and z, right? Which means that when we change them the first time, this means for 3 amounts of the x basis vector, 3 amounts of the y, 1 amount of z in this first new basis vector. This tells us the second basis vector in terms of x, y, and z. And this tells us the third new basis vector in terms of x, y, and z. So now our basis vectors are changed to this matrix's columns, right? But now we have to apply this one. Now the way we do that is this tells us the amount of the first basis vector in our new first basis vector. Whereas before, the current first basis vector was x. Now they've been changed. So the first current basis vector is this changed one here, right? Because don't forget, we've already changed them once using this matrix. So by default, they're not X, Y, Z anymore. They're now these three. So this column here, if we take it individually, means we have one amount of the first basis vector, which is now this, 3 amounts of the second basis vector, which is now this, and minus 1 amount of the third basis vector, which is now this. And we can do that to each column. And I've written out the calculation for you. So we might have to do a bit of back and forth to check. But if we see this is 1, 3, minus 1. Oh, sorry. This has 1 amount of the first new basis vector, 3 amounts of the second, minus 1 of the third. And then likewise, let's do it one more time. 0, 2, 3. So 0 amounts of this, 2 amounts of this, 3 amounts of this. And you can see 0 amounts of it, 2 amounts, minus 1. So then using this, you can rewrite or basically transform each column of, each column of the right matrix, right? Using our new current basis vectors. The key to remember, and I'll say this one more time because it's really important, is that we realize once we've already changed the basis vectors using this matrix, the current ones are not X, Y, Z anymore. They are the columns of this matrix, which is what we've changed them to. So now we've putting these columns, new columns together, we get a matrix which combines the transformations from both. So it combines the transformations from the left and the right. So now I've realized I made a little bit of a mistake with my calculation here. I had a minus 1 here when it's supposed to be a plus 3. So this should be the new correct second basis vector for our matrix here, which is a combined transformation matrix of our 2 individual transformations here. So we've combined them to get this new matrix. So then when we apply this to our vector 2, 3, 4, we get the effect of both consecutive or successive matrix transformations. So we should have 2 amounts of the first basis vector, 3 amounts of the second, and 4 amounts of the third to get this vector here as our result. And what a beast of a result that is. The last thing we want to cover is rectangular matrices. Now, we've been quite lucky so far. We've only seen matrices which are perfect squares. The amount of rows are equal to the amount of columns. But what if that's not the case? Here, our matrix has 2 columns, but 3 rows. Okay, well, let's see what effect this has. So we have 1 amount of the first basis vector, 2 amounts of the second basis vector. So when we add them, our result has an extra basis vector than it did when we started. By default, we had 1x, 2y. Now we have 8x, 5y, and 7z. So somehow the z's come in there. And the reason it's done that is because our basis vectors here have an extra component to them compared to our initial vector. Now you may be thinking, well, doesn't this maybe violate what we've said before, where the number of basis vectors in the matrix have to be the same as the vector? Well, look, remember we've said the amount of columns has to equal the amount of rows. This has 2 columns and this has 2 rows. So it is perfectly fine, but it just ends up adding another dimension as a result. If we look at this example, it does the opposite. As you can see, 1 amount of the first, 1 amount of the second, plus 1 amount of the third gives us 5x plus 10y, where we had x plus y plus z. So as a result, our z vector is gone. We now have 2 basis vectors left, where before we had 1. So rectangular matrices, they still work, but they may add or take away a dimension from your matrix which you apply it to. So one last quick thing for us to go over is when before we were talking about successive transformations, so one matrix followed by another, it's really important to realize that the order we apply the matrices matters. So in this example, we first will start by applying this matrix first, followed by this one, but then below we do them the other way around. Now as you can see, where each of these calculations is calculating each column of this matrix. So for example, for this first column, we do 3 lots of 1, 2, plus 4 lots of 0, 4, and that gets that first column. We find that our matrix result for the top row is completely different from our result for the bottom row. So really make sure if you ever do a question or a problem like this, you do the right matrix first. So that's all for my video on vectors and matrices. I really hope you all enjoyed and you gained just a little bit of a deeper understanding of these topics. In the future, I'll definitely be making more videos just like this on topics maybe similar, more fundamental topics, and some more complex ones too. So I really hope you enjoyed. If you did, then please like, subscribe, and comment down below. It would really mean a lot to me. And if you have any suggestions on anything you'd like me to maybe improve on, or any videos you'd like me to release in the future, please let me know. So thank you very much for watching, and adios.